Okay, let's get started. So I don't want to delay too much on the schedule of this morning. So good morning to everyone. My name is Matteo Cococcioni, for those of you whom I haven't met yet. And today there will be me and Nicola Colonna, which I don't see now anymore, in the back. And we'll be on duty to tell you some difficulties of DFT and usual ab initio methods that you use currently. So after the yesterday's session where you learned or reviewed, if you did know before what DFT, density functional theory, is based on and how it works, today it's our duty to show you that in some cases it has some problems, and so you want to keep them in mind. And so it's also our goal today to discuss some possible fixes, okay, some methods to take care of these difficulties that usual approximation to density functional theory, because keep in mind it's in theory an exact one, to discuss what these approximate fixes to the approximate functional do, and to show the range of applicability, when you can expect them to help with this problem that you have with approximate function, when you cannot, and what kind of improvement you can expect from them. Okay, so I will be presenting in the first part of the morning up to the break, coffee break at 10:30, and we'll mostly discuss about the so-called DFT plus Hubbard correction, DFT+U. Nicola later on in the second part of this morning will present other corrective scheme that has been formulated over the years. Okay, so this is the outline of the first part of my part. So I will go over very quickly what we saw yesterday, in particular the theory of density functional theory. Discuss briefly some approximation, the most used ones, and also review success stories of these. And then the main topic, as I mentioned before, will be notable failure, okay, of these approximations. And specifically, I will focus on those that stem from defective representation of so-called electronic correlations, okay? So that's especially important when you have electrons that are likely to localize on very localized states. So that's when correlations are important. That's when you can expect usual approximation to the exact density functional exchange correlation energy to work the worst, okay? So to have the most problem. And then I will introduce the so-called DFT+U functional, discussing what it is, how it works, and again some stories of success of these easy, this simple correction to the approximate DFT functional. In the second part, I will present what the meaning of this Hubbard parameter, the effective electron-electron interaction, is, how it can be seen, how it can be computed, and I will also show a way to compute it from linear response, which is something that we will also work on this afternoon. Okay, so this afternoon we'll focus on doing DFT+U calculation, so applying this correction to standard ground state calculation from DFT, and also on we'll practice on how to compute the effective Hubbard parameter from linear response, first principle linear response. Then in the next part, I will also present some extensions to the usual formulation, let's say, of DFT+U, which will give us, I hope, an opportunity to understand it better, the theory that's behind and the range of applicability. So what you can expect, what you cannot expect from to be solving when using this kind of correction to standard DFT functional. And then I will, at the end, if there's time left, I will rapidly present what we're going to see this afternoon, what we're going to work on, or otherwise I will directly present it at the beginning of the afternoon session if there's no enough time left. Okay, so let's review quickly what we saw yesterday about density functional theory. Okay, so you probably, and I hope you probably remember that the main advantage brought about by density functional theory consists in the fact that to solve the electronic structure of a material, you don't need to deal with the very complicated object that you have on the left, which is the many-body wave function, which of course depends on 3n space variable, where n is the number of electrons in your system. But you can focus instead on the charge density only, which only depends, of course, on 3 space variables. So it's a much simpler object to deal with and probably leads to a much simpler calculation. This possibility is, of course, brought about by the one-to-one correspondence between the external potential acting on your system and the ground state density that yesterday Stefano Baroni illustrated in his first talk. This is due again to the convexity or concavity of the energy as a function of rho that established this one-to-one correspondence, which is otherwise known as the Homberg-Kohn theorem. This correspondence allows, of course, to see every ground state properties as a functional of the external potential, or equivalently of the ground state density. Okay, and in particular, this is true for the total energy of the system. So the important piece that makes density functional theory a practical tool, the first piece, is the possibility to write the energy, the total energy of your system as a functional of a universal functional that describes kinetic energy and electron-electron interaction. Okay, and also the fact that this functional is variational, which means that if you minimize it with respect to the density, you get the ground state density and the ground state energy of your system. Okay, so you see here how it's usually expressed. This is the external potential, the interaction of the electrons in your system with the external potential. So if you are in a crystal, the external potential is nothing else but the interaction of the electrons with the ions of your system by a Coulomb attraction. And what we put in f of rho, this universal functional, is the sum of the kinetic energy of the electrons, the classical density Coulomb repulsion, and everything else that's closed in this exchange correlation functional. Keep in mind that also already this way of writing f of r is using what Professor Baroni discussed yesterday. So this idea of mapping everything onto the ground state problem of a non-interacting system, or non-interacting electron system. In fact, this T0 is the kinetic energy of an independent electron system. It's a system of electrons that don't interact with each other, having the same density of the real one. Okay, and this is the interaction, the Coulomb interaction you can write between two distribution of charges that are are corresponding to the charge density that you have, the charge density of the real system. So this function is designed in such a way to mimic the total energy of the real interacting system, but allows you to work with the independent electrons, which makes your life a lot easier because you can write explicitly what this kinetic energy is, and you can derive Kohn-Sham equations from there, which are single particle equations. Okay, these single particles will be will be based on single particle wave function, the so-called Kohn-Sham wave functions, that are the ones that you can use to construct the density. Okay. And the exchange correlation functional should contain the difference between the real interaction between electrons and all the pieces that you have added here. So the difference between the real kinetic energy and the one of the independent electron gas at the same density, and the difference between the real interaction energy and the one that you express this way with the so-called R3 term. Okay, so this is basic DFT. So in principle, we know DFT is an exact theory. It's just a way to rewrite things in a more convenient way. But in practice, what the exchange correlation functional is, nobody knows. So nobody has the recipe to the exact exchange correlation functional. Okay, we have ways to express it in a formal way. One of them is given here. So you see this one here is based on the matrix element of the kinetic energy operator and the Coulomb repulsion operator over many body wave function. Okay, and then you take the minimum over all the many body wave function that corresponds to a given density, because at the end of the day you want a functional of the density. Okay, that's your unknown variable. Okay, so you suppose you can do this. You can suppose you can screen all the possible many body wave function corresponding to that density. You take this expectation value, you minimize over this range of many body wave function, and then you subtract what you have explicitly added in your equation on the previous slide. Okay, that's what defines formally the exchange correlation function. Nicola this afternoon, later on this morning, will present other ways to express it that are maybe more pliable to define some approximation, some approximate expression for the exchange correlation functional, but this is one of them. Of course, this is of little use, because if we knew what the many body wave function would look like, even at given density, we wouldn't need to solve density functional theory. Maybe we would be able to just solve the Schrodinger equation for the many body problem, and that's it. So, so as I said, this needs to be approximated. Okay. So in order for density functional theory to become a practical tool, you need to define some approximation to this term, and there's been a lot of work, a lot of scientific work on this since when the middle 60s, when DFT was first introduced and defined. Okay, so this has been a very important work. What are the most common approximation? There's certainly the local density approximation and the generalized gradient approximation. So the local density approximation is based on the homogeneous electron gas. Basically, it's based on saying that on supposing that the exchange correlation energy density, okay, the quantity that would give you the exchange correlation energy once you integrate with the charge density, is the same as the one that you compute for the homogeneous electron gas at the same density. So it's the same. If I focus on a point of space R, okay, and I have a rho of R at that point, then I can say, according to this local density approximation, that the value of the exchange correlation energy density at that point is the same as the homogeneous electron gas would have for a charge density of the same value at that point. Okay, so that's called the local density approximation. A refinement of that takes into account not only the charge density at the point of interest, but also of its gradient, the modulus of its gradient. Okay, that is a way or a first approximation to try to account for some variation of the charge density, or if you want some known locality. Okay, the first piece of information you need to take into account if you want to consider the way the charge density is changing in this point of space you're focusing on is the gradient. So that's why they included the gradient in this expression. And of course, there are a number of different, the LDA is sort of unique. So once you know what the homogeneous electron gas exchange correlation energy density looks like, that's the one that you should use here. There's been a lot of different definition instead on for the GGA one. So you get, for example, PBE is one flavor of that very commonly used one, PW91, and so forth. All of these have been different formulation. The people working on that try to satisfy some conditions on that, try to constrain these mathematical objects in such a way they satisfy some physical condition in certain circumstances. So this is not something that we focus on today, just to say that, to remind you that the exchange correlation function is something that's usually approximated in one way or the other, and that's a choice that you make when you start your calculation to use one function or the other. Okay. So I don't want to give you a wrong impression. DFT has been a very successful computational tool over the years and has been working probably surprisingly well, even beyond the expectations, especially for systems, of course, that have almost homogeneous electronic charge because of the approximation I mentioned in the previous slide, but also for systems that do not have such an homogeneous distribution of electrons in themselves. So, for example, if you're looking at the properties of diamond, you see how well, for example, phonons have been reproduced using density, some approximation of density functional theory. The dots are the neutron experiments, and the lines are the results of calculations from DFT. And also, this is the dependence with temperature of the bulk modulus obtained using the so-called quasi-harmonic approximation. So you can see how well they correspond to one another. Another example could be also the variation of volume as a function of pressure for materials. These are, I think, magnesium silicates of the Earth interior, and possibly containing also impurities of aluminum and iron. So quite complex perovskite systems, and that's again how well experiment and theory agree with each other. So it does work quite well, not always, unfortunately, and there are many cases where this agreement with experiment is not there, so you cannot be expected. One paradigmatic case of when you have problems with density functional theory is represented by this transition metal monoxide that typically have this rock salt structure, but also present a rhombohedral symmetry because of magnetism. You see that most typically what they what they have is an antiferromagnetic ground state with alternating ferromagnetic 111 planes of opposite sign, of opposite magnetization to their neighbors. Okay, so this gives the structure rhombohedral symmetry. And however, if you try to compute them with LDA or GGA, so more standard approximate exchange correlation functional, you typically get a poor estimate of the structural properties. You get an underestimation of their magnetic moment. In some cases, for example, iron oxide would get a ferromagnetic ground state instead of an antiferromagnetic one. Magnetization is underestimated, as I said, and if you have compared the energetics of different states, you typically get the ordering wrong. So it's not something that you can neglect. So these are substantial errors that you run into with this material. And of course, if you look at the density of state, for example, although from experiment you might expect an insulating ground state, these are typically insulators, you get a metal. So you get some finite blob of density of state cutting the Fermi level. Okay. We'll see this is not wrong in principle for density functional theory, but needs to be understood, needs to be handled with care, this kind of situation, especially when you have electrons in narrow d states, and especially if the states are degenerate, like in the case of iron oxide, which we'll discuss later on in some detail. And also, if you look at structural properties, for example, iron oxide undergoes this rhombohedral deformation when under pressure. You see that this deformation is overestimated by something like a generalized gradient approximation. Okay, so it should be, this is the rhombohedral angle, basically the angle between this solid line vector here. 60 degrees corresponds to the cubic structure. Lower than 60, it means that this cube elongates along the 111 diagonal. So imagine to pull the two corners away from each other. That's the kind of deformation that you get if this angle is lower. So experiment says it's a little bit elongated along the 101, but DFT says, the approximate DFT says that this elongation is higher. Okay. So this is one example of problematic case. Another one is the localization of electrons over defects. So this is cerium O2, oxygen 2, and here you get an oxygen vacancy. So there's one oxygen mixing. So you would expect that the two electrons that are left behind by the oxygen that's missing would localize on two of the 4 cerium atoms that are around this oxygen vacancy. It's not the case. So you see the charge density of the 2 electrons here that are left behind that are delocalized instead over 4 cerium atoms. Okay, in a sort of what is a sort of metallic state. This is again not consistent with the experiment. And if you use a standard approximate DFT to represent this kind of system, you run into quantitative mistakes, so quantitative errors. So imagine these systems are typically used in considering in catalysis. So the energetics of reaction might come out wrong if you don't fix these kind of problems. Just because the electrons is not, the 2 electrons that are left behind by the oxygen mixing are not behaving as they should. Okay. And let me give you, this is to remark that that using DFT is not really always okay, not even for properties like equilibrium crystal structure that one might expect to instead work reasonably well, even if DFT fails. Okay, so sometimes in literature you find, okay, we have this transition metal compound. We know DFT doesn't capture the energetics of electrons or the distribution of electrons. However, we assume that it's working relatively well to predict the equilibrium structure, for example, or other simple properties. It might be the case, but it's not a rule. So don't take it as a rule, and this example should show you that instead you might end up with a very wrong prediction. This is another case that's something that actually I'm working on, cathode materials of lithium-ion batteries. Okay, these are also transition metal oxide. In particular, I'm working on these lithium transition metal phosphate olivines, which means that they have orthorhombic structure. And the problem here is to capture electronic localization independence of the amount of lithium that you have in your structure. Okay, so during the discharge of the battery, lithium moves from the anode to the cathode. So you have a different amount of lithium ions in the cathode along the time, during the discharge of the battery, and you see that the cathode material switches from this state, which has no lithium inside, to this other phase that has plenty of lithium inside, and correspondingly, the transition metal switches from 3+ states, if you do the math of the stoichiometry, to the 2+ states. And this switch is actually what powers the battery, okay? The redox energy corresponding to this change of state is what provides energy or difference in the chemical potential for lithium, which is what drives lithium from one side to the other, and the electrons also through the external circuit. The problem is capturing what happens when you have intermediate amounts of lithium. So during the charge or discharge of the battery. Because nominally here, for example, if you have half of the total lithium, you should get on average 2.5+, which is not really physical valence state, oxidation state. So what happens instead is that some of the iron or some of the manganese or whatever metal you have here are 2+, and the rest is 3+. But to capture this state, which is very important, as we'll see for the energetics, implies to localize electrons on on a subset or a subgroup of those transition metal ions. That doesn't happen automatically, and doesn't happen with standard approximate DFT functionals, exchange correlation functional, even though by symmetry or from the structure, the ions are already can be already classified in two different groups, because, for example, the different distance from the present lithium ions. Okay, so this doesn't happen, and I will show you how. So instead, with approximate DFT, you get 2.5+ oxidation state and a metallic ground state, because the electrons goes around and spread out over this transition metal, and because this is due again to the overstabilization of metallic ground state with electrons spread over, due to the approximation used on the exchange correlation functional that are again mostly oriented to the homogeneous electron gas. You get formation energies and average voltages that are in disagreement with the experiment, and also equilibrium structure and magnetizations and other properties also come out wrong, or somewhat wrong compared to the experiment. So you cannot really trust what you get from standard approximate DFT exchange correlation functionally for this case. Here's what I meant by compromising the energetics. So the formation energy of the intermediate lithium compound is this total energy difference that you have on the first line. The average voltage is measured like this, like expressed in this formula on the back. So you see that for the iron compound, you get a positive formation energy, which means that the intermediate lithium compound is not thermodynamically stable, while instead is predicted to be stable by DFT. So DFT would stabilize a material with half lithium in it. And you see the voltage is significantly underestimated from, with respect to the experiment. Same thing for the manganese compound, although DFT here does a little better job in predicting that no intermediate lithium material forms. Okay, so other problematic materials, there's plenty of them. Okay, so in general, you should handle with care transition metal compounds, especially like in cases like these ones where you have mixed balance transition metal. So for example, this is a very famous example, magnetite, so iron 304, the first discovered magnetic material. If you do the math of the oxidation state, you will end up with a third of the iron being in 2+, the other two thirds being 3+ states. However, it's difficult, if you do a DFT calculation, it's difficult to get this from your calculations right away with standard approximate exchange correlation function. You would get, again, electrons delocalized on all the irons, and all the irons approximately at the same valence state. So not differentiated as they should from one another. Other classes of problematic materials are, for example, ITC superconductor, especially in the doped phase when you have impurities in the buffer layers injecting some charge onto the copper oxidant planes, and the kinds of phenomena that these typically gives rise to cannot simply be captured by DFT, standard DFT approximation. Also materials that have so-called metal to insulator transitions, like these are famous, again, example, BO2 oxides of this kind, that because of structural transition, they make also a transition, an electronic transition from an insulating to a metallic state. This is also difficult to capture with DFT, with standard DFT. So there's not a common rule. I mean, it is not a rule to understand when a material is problematic, but in general, if it has open shell D or F states, expect some trouble from using approximate exchange correlation function. Okay, so open shell means that the D or F shell is not completely occupied and is not full, and there is some degeneracy because electrons could occupy some of those states and leave some other empty. And if the symmetry is sufficiently high, then you could be in trouble. So if the symmetry is not broken by other stuff like crystal field, electrons might not know where to localize and may fail in doing that. Other famous problems that you get into when using DFT is related to molecular dissociation. This is very well known, very well studied from a long time. Here are some examples from literature. So if you're trying to compute the binding energy of H2 molecule while you're breaking it apart, so imagine to pull the two hydrogen apart from each other and study the energy. What would you find? So here's what you find with tree approximation. The black line is is what you get from LDA. The red one is R3-FOC, okay? So you're not breaking the spin symmetry, no symmetry breaking here, and that's what you get. So you see that instead of going to 0, as they should, the reference state of the two atoms apart from each other, you get to some positive values. And this is due exactly to lack of correlation. So the defective account of electronic correlation, strong correlation. What H2 is affected by is called strong correlation. But the problems remains even if you get a one electron system like H2+. H2+ has two nuclei, 2 protons, and 1 electron. Okay, so you might think, okay, we get into troubles when we have many body systems like 2 electron system like the one on the left, but we should be safe with 1 electron system because we're using a theory that should supposedly good when you have single particle limits. Instead, it's not true because, again, there should be an exact cancellation between exchange and direct Coulomb interaction, which is not in place in DFT. So there is some residual interaction that prevents this system to have the correct energetics. So you see, physically these are two very different problems. Here you have no correct account of correlation. Here you have some residual interaction between electrons, so-called self-interaction that shouldn't be there and is there, but they both descend from the approximation that you have used in the exchange correlation function. Okay, so the fact that you're using some approximation there gives you these wrong results. If we want to understand a little better what this is, we should probably go back to the work of John Perdue and co-workers, Melody and other people, the work they did between the end of 70s and the beginning of 80s, studying a lot these kinds of problems. Like, for example, the dissociation of an heteronuclear molecule like XY, so XY being two generic species different from one another. You see that they demonstrate in this paper here that I strongly recommend you to read that the total energy should have a piecewise linear behavior as a function of basically the number of electrons you have on either fragment of the molecule. Okay, and this is so because you basically have a statistical mixture of two states with one mixing the states where the electron is on one fragment or the other. So if you do a linear combination, of course you get a linear behavior of the energy in between these two extreme cases. What you get from approximate DFT, of course these two curves are describe the energy in two different distances. The one is at the infinite distance, and the second one is when the dissociation takes place. Okay, so the distance where the dissociation takes place, and since the x is the less electronegative one, it loses one electron. So there's no, basically at that critical distance, there's no difference in energy between the electron between the neutral configuration and the one where you have the electron moved from X to Y, which is this one, so the ionic configuration. Okay. But in any case, if you do this calculation with a standard DFT, instead you don't get this piecewise linear behavior. You get an analytic behavior of the energy as a function of the number of electrons. And that makes you lose some important quantities that relate to the discontinuity of the first derivative of the energy. That is this finite jump in the derivative, which corresponds to the difference between ionization energy and electron affinity. This is what chemists call the fundamental gap of a system. Okay, so the or single particle gap of a system. So that's what you're missing. What you're missing if the total energy has an analytic, continuous behavior, continuous with its derivatives. So how do we understand this? So we might do a mind experiment and try to describe what happens if we use DFT to describe the energetics of for example, H2 molecule when we try to separate the two nuclei from one another. Okay. So if you had an exact theory, that's what you would see. Okay. So at certain point, at certain distance between the nuclei, you would see that the charge localized on either one, and you expect to produce two neutral fragments, so two isolated hydrogen. Of course, the spin wouldn't matter, so all of this configuration would be equally good, and even the ones that have parallel spin, so would all be degenerate in energy. Okay. But from the point of view of the density, you would have equal probability to have spin up here or spin up here, doesn't matter. Okay. If you do this with DFT instead, you get something like this. So no matter what the distance between the two nuclei is, if you don't break the spin symmetry, you always get half of spin up electron here and half of spin up electron here, and the same thing for spin down. This is effectively described like a metallic state, because the only way you have, without breaking the symmetry, to get alpha spin on either side is to obtain a metallic band, an half field band for each spin. Okay? This is not wrong in principle, because remember, the DFT is supposed to give you the right ground state properties, the right ground state density, for example. And the fact that you have alpha spin, alpha of each spin on each side, basically, conveys the fact that you have equal probability to localize them on either nuclei. Okay? So it's not wrong in principle. The problem is that the energy is not the one that you would expect or you should obtain, which means the linear combination of the two energy in the exact limit. While instead, with DFT, you get something different, and specifically you get an energy that is lower than this linear combination. Okay, so you get something that's, I never remember how to call again, concave or convex like this, instead of having the straight behavior. So that's what localizes electrons in this unphysical intermediate state, which is not what you want. So in a sense, if you want to characterize this kind of problem, you can say that the curvature of the energy profile is exaggerated, is overestimated. And that's some of the origin of many of the problems that you get into with approximate exchange correlation function. That's another pictorial representation of this problem. So you get with DFT, you get an analytic behavior of the total energy, but you know, as I showed in the previous slides, the physical behavior is a piecewise straight, piecewise linear. Okay, and what you're missing here is this derivative discontinuity that should in fact be a feature of the exact exchange correlation potential. So the exact exchange correlation potential has this sort of discontinuities when you switch from an integer value of electrons to another, to the next one. And this reflects also in solids. So a well-known problem of DFT that was mentioned also yesterday, I believe, yesterday morning by Ralph, is the fact that if you look at the Konsham spectrum, like I'm doing here, plotting the silicon band, you get a gap that's lower than the experimental one, the single particle one, by almost 0.5 electron volt, which is a significant fraction of the band. So this is it should be 1.1, and instead you get 0.5, 0.6 electron volts. Now this shouldn't be looked at in principle because again DFT is a ground state theory, and is not supposed, is not bound to give you physical single particle energy. These don't mean much in principle. Those are just you remember what we do to get this is solving a single particle Schrödinger-like equation, the Koopmans equation, but these single particle wave function are not bound to any physical meaning, nor are the eigenvalues that we get. So the single particle eigenvalues are not bound to mean anything in DFT. The only condition that should satisfy is that they should give us the right ground state charge density. That's the only one. However, if we had the exact functional, we would be able to get the exact single particle gap, and that would be the one that you read from this spectrum, the Koopmans spectrum, plus that discontinuity I mentioned in the previous slide. Yes, the discontinuity of the exchange correlation potential. So the sum of these two quantities is bound to give you the correct single particle energy gap. Single particle, I mean, this is the difference between photoemission, inverse and direct, or between ionization potential and electron affinity. So it does not contain the exciton effect when you excite an electron from valence to conduction band. Okay, it's not an optical gap. That's an extra effect you will learn about how to compute it next week. Okay, so this is the situation. So let's now start discussing what DFT+U, this Hubbard correction to DFT, does, and how it is structured. So I'm a little late actually, so I will try to speed up a little bit from now on. Feel free, on the other hand, to ask questions if you have. Every now and then I will have summary slides, so that may be a good point for you to ask questions if you want to. So the general idea behind DFT is quite simple. So as I mentioned before, you expect problems when you have electrons on not completely full D or F shells. And in these conditions, according to the DFT+U idea, we want to treat them using Hubbard Hamiltonian. So the Hubbard model is something that people use to study the behavior of these so-called strongly correlated electrons. So the idea is that to embed this Hubbard Hamiltonian to work on these localized electrons. So this is the general formulation. You have the DFT energy functional. You add an Hubbard energy functional that works on the density of these localized electrons. You subtract something that to avoid the so-called double counting effect, because some of these correlation energy that you supposed to describe well with this Hubbard Hamiltonian are already contained in here, so you don't want to count them twice. And so this is the general idea for correcting the energy functional. And specifically, the first formulation had the simplest one, so the product of electrons on the same atomic site or neighbor atomic site, and that's how you represent the double counting term as a mean field approximation of the previous term. And as I said, this Hubbard Hamiltonian works only on the specific D and F states. So in order to obtain that, you project the Koopmans state onto localized state, and get from this projection you get how do you say a localized occupation that you use in this piece of the functional. Now, the general formulation of this Hubbard Hamiltonian is borrowed from the R3-Fock expression, R3-Fock functional. So you see the direct interaction between electrons of opposite spin, and then if they have the same spin, sigma and sigma, they have parallel spin, you correct that for the exchange term. Okay, this is nothing else or nothing different from what also R3-Fock does. You might be surprised that we use some R3-Fock-like expression to correct the physics of supposedly correlated system, because R3-Fock has no correlation by definition. Correlation is everything that's beyond R3-Fock. Okay, so you might be surprised, but we're still working with the single particle quantities here. So we don't have for product of four creation or annihilation operators. So that's what we can do within this approximation. And that's the expression of the double counting term. So this is appealing because it's rotationally invariant. So if you change the definition on the same atom of the d states that you're projecting on, I mentioned before that you have these phi I m states defined for the atom I. Okay, if you change the definition of those states, which means if you rotate, for example, the basis set you're projecting on the same atom, you get the same correction. So you get an equivalent description of the same physics. Okay, just because the interaction change accordingly with the same rotation matrices. So basically, this expression is covariant for rotation of the yes. No, in the previous slide it was not, yeah, the first formulation was not rotational invariant, so it was only introduced in 95, this refinement. Yes, yeah, yeah. So if you rotate the basis set you're projecting on, you get another number. Yeah, but typically nowadays people use this one, so for obvious reasons. We don't actually, I mean, this is implemented in Quantum Espresso, the full one. Most typically we use a simplified one. I will skip all these. Basically, it stems from the previous one by neglecting anisotropy. So neglecting the dependence on higher order spherical harmonic of the effective interaction. So you get this expression here, where this is the total correction that you add to the DFT total energy. So you see as depends on only one parameter, atomic parameter, and it's based on the trace of this occupation matrix times 1 minus the occupation matrix. Okay? So trace of n, 1 minus n. And since you have a trace here, you still have a rotational invariance, because the trace is a rotational invariant quantity. Okay, so if you change the definition of if you rotate again the wave function, the localized wave function you're projecting on, this piece doesn't change, or you get at the end the same energy in the same an equivalent description of the localized electrons. So this is the one that we are working on, and we will stick to this expression for the rest of this talk, and also for this afternoon session. Okay, this is the one we will use. So in order to understand how it works, it may be useful to compute the potential that stems from there. And for doing that, we can use a diagonal representation. So put ourselves in the basis where the occupations are diagonal. So lambda are the eigenvalues. So you see you get the sum of lambda times 1 minus lambda, which means that you have an energy penalty for everything that's between 0 and 1. Okay, a positive energy penalty. So these terms will encourage basically localization. So it will encourage this eigenvalue to be either to polarize, either 0 or 1. So, okay, that suppresses what's in between, the fractional values. So if you compute the potential, the pieces, the potential that goes into the Koopmans equation, you get something like this. So you get a term that's attractive when you have more than half occupied states, and that's repulsive when you have less than occupied states. So if a state is little occupied, try to empty that state. If instead is more than half occupied, tries to get the entire electron on there. That also opens a gap naturally in the Koopmans state, because it puts an energy difference between occupied and unoccupied states. That's how it works. That's why using this simple correction, you can expect the opening of some gap around the Fermi level. Okay, how do the problematic cases I started with change with the use of this correction? So we started from this metallic delocalization of the extra charge around the defect, and now you get a localization, as you would expect, of the 2 electrons on 2 cerium atoms around the defect, the oxygen vacancy here. So that's described in this paper from 2005. And you see also that the last, the electrons are, if you do the density of state, are localized in this gap state that forms because of the oxygen vacancy that you created in the structure. What about this case? Yes?
Sorry, I agree with that. When the student after the time one state of the orbital or the whole orbital is occupied. That's why I say we take the orbital.
Mm-hmm.
So we have different orbital. So we take the whole orbital.
No, it's one by one. So yes. So in fact, I used the eigenvalues of that occupation matrix. So you get the sum, I remember, of lambda times 1 minus lambda. So it operates on each of them separately. Although it's written, I mean, the correction is the same for all the states of the same atom. It's the same for all these states of one atom. Then the action of this potential on each state depends on its occupation. So it's attractive if it's more than half occupied, it is repulsive in the other case. So do we correct this case? So do we get a collection of 2 plus and 3 plus? Well, we get closer at least to that. We correct in the right direction. So you would expect, so this material with plenty of lithium has 2 plus iron, this other one has 3 plus iron. So when dealing with this, the half lithiated one, you want basically 2 plus being described like this. We have the same amount of electron as this, and 3 plus the same amount of d electrons as this. And you see this is not true for standard DFT approximation. They're actually quite close to each other, so approximately 2.5 oxidation state, but you get closer when using this correction. So you get a 2 plus like a 2 plus and 3 plus very close to the 3 plus. So you manage to localize electrons. We will see also this in the exercise this afternoon. So we will have a chance to directly see from the output. And also energetics changes a lot in the right direction. So you get positive formation energy for the intermediate lithium compound, and also voltages that are much closer to the experimental value of 3.5. Well, I'll have to skip on other application that we did over here because I guess there's no time. This is a recent thing that we did, the extension of this Hubbard correction to the phonon code that you will learn about, I think, either tomorrow or the day after. I won't have, again, time to review the implementation, the details of the implementation, but I want to show you the effect of this Hubbard correction on the phonon dispersion of materials in this class. Like, again, these are two transition metal monoxide, manganese oxide and nickel oxide, and you can see that the DFT GGA results are the black dashed lines, and the green ones, the green solid ones, are the results obtained with the U correction. So you see a significant shift on the vibrational energies of these materials. Specifically, you see these big jumps, the correction of these big splittings between transverse optical modes that you obtain with DFT. These are due to the magnetic interaction, that because of the delocalization of electrons are overestimated in DFT. This is another effect that you get. So the delocalization of electrons sometimes leads to the overestimate of intersite magnetic interaction. So the interaction between localized moments on transition metal ions. And these being overestimated, you get also a bigger splitting between transverse optical modes than you should get. So this gets fixed. So you compare this black arrow with the small blue one here. And so the better localization of electrons on these states of manganese or nickel also leads to this effect, besides the better agreement with the experiments. So, so again, don't give for granted that with standard DFT you can capture structural or vibrational properties, because that might not be the case. Well, this is another example of what I just said. This is an alloy that has a martensitic alloy, so a martensitic transformation that goes from austenite higher temperature phase to martensite lower temperature phase. It turns out that this one specifically has a modulated martensite phase, so the non-modulated one that you have here, the tetrahedral one, should not be stable. I mean, this should only be stabilized when excess manganese is inside some manganese replace also gallium. However, the energetics is very delicate, so they are very close in energy, these two phases. So if you compromise the description of magnetic interaction between manganese, you may end up with the wrong ordering. So because of these two energies being close to each other, the part of the energy relating to the magnetic interaction between manganese is very important, and if you get that wrong, you might get the wrong order, and in fact that's the case. DFT+U corrects that because corrects the better localization, lowers the magnetic interaction between manganese ions, and corrects the relative stability of the two phases. Okay, that also works if you consider excess manganese in the formulation with respect to the stoichiometric formulation. So when manganese substitutes some gallium atom, this phase, non-modulated martensite phase, is expected to get stable, and that's what you get here. So you will get a threshold value of manganese concentration beyond which this martensite becomes more stable. While instead with DFT, you always get it more stable, and this even more so when you add the manganese to substitute gallium. Okay, the iron oxide deserves some attention because it's significant regarding the symmetry problem. So if you apply DFT+U, you might get, you remember we got the metallic ground state, which we were not happy about because it's known to be an insulator. However, if you apply the U correction, you get a gap, and so you might You might be happy about that because you got an insulating ground state and maybe you expect the properties to be right. And in fact, some properties do turn right, like the insulating character, the antiferromagnetic ground state, you now can stabilize that. And you might also get the rhomboidal distortion. However, if you apply the +U correction as it is, you get this line. So you get, instead of an elongation of the cubic cell along the diagonal, you get a compression, basically, which is not right. The reason is that the D states, where the triplet D states, where the last downspin electron of iron sits on, which gives the metallic character when you have within the standard DFT approximation, gets split because of crystal field in two groups. One with one state, and the second one is a doublet of two states. Okay. Now the DFT solution is a metallic one because localize these electrons on this doublet of states. So you get half filling of that band that gives you an effective metallic state. And the DFT+U solution that you can easily stabilize, it corresponds to getting the energy of these states lower than the other two and putting the electron there. So that's a gap that originates just from crystal field because of this, the splitting between these two groups of states. And actually these terms are not to be right because, and as I showed you before, the distortion is not the one that you expect from experiment. What's going on here, basically? This can teach us quite an important thing. So this is the +U solution when you localize the single electron on the state that's remained single, okay, after the crystal field splitting. But nobody tells us that instead another picture is the real one. What if the metallic state that we get from DFT is actually a linear combination of two insulating states? Okay, suppose that the degeneracy of these two states is only effective. I mean, is only true on average, while instead we can have two insulating states with equal weight, okay, where you localize electron on either one of these two, like I showed you here. You get a different symmetry state. So the last electrons would localize on a z-square state along the 111 in the first case, or on a planar state on the 111 plane in the second case. And turns out that the overlap of the two, of course, would reproduce the metallic behavior that you get in DFT. And if you go look at the energy, you see that the second one is more stable. And in fact, also produces a better agreement with the experimental distortion of the cell under pressure. So that means that a metallic ground state obtained from DFT can sometimes be thought of as a combination of insulating ground state where you occupy different single particle states. And that's a feature that stems from the correlated character of the ground state of this material. So you won't be able to capture this. It's like the dissociation case, right? So if you don't break the symmetry, you get always a metallic state. But that metallic state at infinite distance should be understood like a statistical mixture of situations where you have electrons either here or there. It's the same here, except that we don't have ions moving apart from each other, but we still have electrons that should decide whether to be on one orbital or the other. Okay, so you get the right energy only if you keep this in mind. Okay, so let me summarize what we've seen so far. So the Hubbard correction to DFT is based on a correction shape on the Hubbard model. I hope this was evident and is understood. It helps in improving the localization of charge and quantities that depends on it, like magnetic interaction. I have no time to review why magnetic interaction should depends on localization, but there are plenty of models that say that it can be expected to work for non-degenerate ground state. Of course, when you have the case of the battery material where you have 2+ and 3+ iron already distinct by symmetry, you can expect it helps a lot localizing electrons on hopefully the right ions. To be used with care in presence of degeneracy, okay? Because that degeneracy might be the same, might be the sign of some significant correlation, something that you cannot intrinsically, you cannot capture with DFT, which is not a strongly correlated method. Okay, so how to compute this U? Of course, the effectiveness of this correction depends on the value of the Hubbard parameter that in most codes, like Quantum Espresso, should be given in input. But what value do we give in input? How wide the gap is that you get in the Koopmans spectrum also is proportional, broadly proportional to this number. So we want a way to obtain this number from hopefully ab initio. So let's go back to the formulation. This is the simplest formulation that we focused on, and you see that the U is a factor of this corrective term. So the strength of this corrective term is proportional to the value of U. And what the U does, you see here, adds a linear part, takes out a quadratic term, okay? So that's exactly what we expect to be doing if we want to take away the spurious curvature of the total energy profile as a function of the occupation, right? So the problem that we discussed earlier this morning is exactly this, and in fact this is exactly what this correction looks like in this representation. So I can understand the U as the second derivative, the curvature of this energy that I want to get rid of, broadly speaking. Another way to understand this is the amplitude of this exchange correlation discontinuity that should be in the exact exchange correlation potential, but it's not in most approximation. This will be useful also later. So basically, I should understand this corrective method like one that tries to impose or to reimpose the discontinuity in some artificial way, of course. This is continuity to the Koopmans potential, okay? So puts back this correction to the Koopmans spectrum of your system and hopefully obtain a better representation of also other quantities once this is done, once this correction is added to the Koopmans spectrum, okay? So we based on this idea that U should be the second order derivative of the total energy with respect to this occupation. Of course, this was derived in the case where you had a molecule dissociating. What's the relation with electrons being on transition metal? Well, if you have transition metal ions in a material, you can think of them because of their localization like isolated units in a bath that corresponds to the rest of the crystal, okay? So you can linearize the energy. Basically, you can aim to linearize the energy with respect to the number of electrons you have on these localized manifolds immersed in the bath, represented by the rest of the crystal. Yes. mean, from the picture it looks so, but it's not exactly so, also because these numbers here are not real electrons. I mean, that picture is a cartoon I use to explain what we're doing, but in practice we're doing mathematically, from a mathematical point of view, something different.
Yes, from the, I guess, from the table of the things that you showed what is doing.
Yeah, also that, I mean, also that is, in fact, also that is an, how do you say, a simplification. So those ions are not really 2+ or 3+, and this, you know, the chemical picture, but you saw that the occupation number don't look like 5 or 6. In practice, this number here look always fractional ones. So it's not really, especially, I mean, if we're dealing with, I mean, if we're dealing with dissociation, of course, you have an integer number on each fragments, and that makes sense. But if you're dealing with the occupation of transition metal ions in a crystal, that number, first of all, it's not uniquely defined, and second, because of also this, it's not bound to have any integer value. Okay, so there's hybridization, always hybridization with the rest of the crystal. In fact, this is a point I wanted to discuss in the rest of this presentation. But let me go on for a few more minutes. So this is the general idea of getting U as a second-order derivative of the total energy. This is actually not the end of the story, because if you compute this quantity, you should take out a finite contribution coming from rehybridization of orbitals. This is not related to electron-electron interaction. This is just the shift on the single particle energies, which is not something that you want to include in this quantity. That's meant to represent instead an effective interaction. So, no, it's not on the graph, but I will show you how to compute this. So the first term, in fact, comes from the self-consistent ground state response. So this will be done in linear response. So you perturb the system, and the first part of this quantity of this expression will come out from the self-consistent response. The second one from the bare response, so basically from the diagonalization at fixed potential, the so-called Kohn-Sham. Will be evident this afternoon also. So how to get this piece of the derivative and how to take that out. And you can read more details in this paper that we did some years ago. So second derivative, how do we compute them? They're not easy to compute, also because we cannot control from input the value of these atomic occupations. Okay, these are results of our calculation. These are not something that we know up front. So what we do, we use a trick basically. We use a Legendre transform. We apply some potential shift. Okay, and then we define a function of this occupation by taking that out after we minimize the electron by solving the Kohn-Sham equation. And so this second derivative that we need is obtained as the derivative of these potential perturbations with respect to the change in the atomic occupation. Okay, so d alpha over dn. Okay. So actually, this is still a bit difficult to get, because again, n is not something that we can control. So something that it's not convenient to have as an independent variable. The independent variable that we can tune easily is alpha, because it's something that we add in the potential as a shift through a projection on atomic states, and so doing the calculation leaves this alpha as an independent variable. So what we do the reverse. So we correct the constant potential with this projector on atomic states of a single Hubbard atom, okay? So we fix this value. We do this for some values around 0, of course, because we need the derivative around 0. And we obtain, from finite difference, the variation of all the on-site occupation of atoms, okay? So this is easy to get from the output of our code, as we'll see this afternoon. From this quantity, we compute these response matrices, the self-consistent one, and the one obtained from basically the first iteration of the perturbed run, because that's the one at fixed potential. And then all we need to do is all we need to do to obtain the U is invert them. Because remember, the second derivative of the energy corresponds to d alpha over dn, while we're getting here the opposite, the inverse. So we need to invert them. Keep in mind that we need to take the difference between the two second derivatives, and this is the final expression. So we'll see this afternoon how to compute this basically interaction matrix here, and how the U is basically the second derivative, sorry, the diagonal part of this interaction matrix. Yes? The projector is a projector on the atomic state. How do you mean? What do you mean? How do you choose? Yes, we typically take atomic orbitals. Keep in mind that it should be consistent with what you do. So if your LDA+U implementation is based on atomic orbital, you should use atomic orbitals here. If it's based on Gaussian, use Gaussian here. So the value of U should be consistent with what you do when you actually use it. Okay, so that's the only constraint. Okay, so let me give you a summary. So fully ab initio estimate of the effective interaction is possible through the linear response calculation of U. This gives you a way to compute this parameter, Hubbard parameter, in consistency of the effective interaction with the definition of the energy function on the on-site occupation. So, and also shows the dependence of this function on everything that you have, on the species that you correct, on the crystal phase, on the magnetic phase that you have, so everything that you have in the calculation. And as I just mentioned, other localized basis sets are equivalently possible. You just need to be consistent. Okay, so. And as I mentioned, this is remember that the plus U thing is a correction. Okay, so you should be consistent with the approximate functional you aim to correct. So you want to correct an LDA functional, compute U for LDA functional, and that's different. Expect that to be to get a different value if you want to correct instead a GGA, ground state. Okay. And once you have implemented the DFT+U, implementing this way of computing the effective interaction is very simple. I mean, it's just a piece of the functional that you already have. And then that I mentioned earlier. Okay, so, well, I have 2 or 3 minutes left. If you give me 5 more, I would like to discuss some extensions. This is done not because we won't see this this afternoon, because these are not yet implemented in the public release of the code, but will hopefully help us understanding a little better what I've presented so far. So that's the purpose of this part, main purpose of this part. So the self-consistent calculation of U. I've shown how to obtain U from linear response, starting from standard DFT approximation, LDA or GGA, okay? But sometimes the DFT+U and the standard DFT approximation are qualitatively different. So for example, in one case you have a metallic ground state, in the other with a finite U you get an insulating one. So you can expect also the response to be different and the U that you calculate from those two ground states to be different. So sometimes you might want to get it self-consistently, meaning that the U should be obtained from a DFT+U calculation. This is not that difficult. I mean, I've shown you that that we get these starting from solving Kohn-Sham equation, which is equivalent to minimize with respect to rho, this functional where you have added this shift in the potential through a projector on atomic states. And then from there you get delta n, computed the response matrices the usual way, invert them, and then from the difference of the inverse you get the U, right? So extending from all this machinery to work from a DFT+U ground state is not that difficult. You just need to get an extra piece in the functional, right? Well, it takes a little detail. You should keep these occupations fixed, because otherwise you get this piece also to contribute to the second derivative, while instead the U is the effective second derivative of only this piece. That's the only little detail that you get. And of course then you have to iterate until the U basically reproduces itself through this iterative process. That's all. Okay. Okay, so I will go a little faster. I didn't mention before that these perturbative calculations should be done in supercells. Okay, depending on the system that you're treating, you have supercell of different kinds. That's so because those are meant to be atomic perturbation that you want to be isolated from their periodic replicas. So you want to put a sufficient distance between a perturbation on one atom and its periodic image in the next cell. That's why you typically need supercells, and you need to converge results with supercell. However, a recent extension of this that we're working on with Yuri Timrov allows to avoid all this using the phonon code that, again, was not yet introduced to you. So basically, instead of working with a gamma point perturbation in the supercell, you can map this gamma point perturbation into a Q-dependent perturbation, but in the primitive cell. Okay, so this is the same advantage that you get when using DFPT for calculating phonons instead of doing it by frozen phonon approximation, which means freezing the vibration of atoms in a big supercell, as big as needed, depending on the wavelength of the phonon that you're dealing with. So that's exactly the same idea here. So instead of having gamma point perturbation in a supercell, you get finite Q point. So basically work with monochromatic perturbation, but in the small cell, which makes the method more automatic and more scalable. So you get a lower computational cost when you scale up the size of the system, and more user-friendly, hopefully. So this is just what I meant earlier. So instead of having single gamma point calculation, you get a finite Q point grid. You generalize the expression of the perturbation, then you obtain the same quantity from these summing over Q points. So summing over monochromatic perturbation you add to the crystal, but described as a supercell, as a single cell, so as small as possible calculation. So instead of having a single calculation on a big cell, you do a number of a Q point grid calculation, but on a small cell. Okay, so that's the point. Okay, now the last point, the very last point is discussing what happens in covalent system. And that goes back probably to his question earlier. What happens for if you apply this +U correction to systems that have significant hybridization? Why do we care about this system? Because as I mentioned before, I hope I mentioned before, the way this +U Hubbard correction works is the following, that it tries to improve the localization of electrons by polarizing the eigenvalues of the occupation matrix, right? So it pushes them to be either 0 or 1, which means pushes the density matrix to be idempotent, basically, okay? And this is done at the expenses of possible hybridization. So how do you get, why do you get fractional eigenvalues from those occupation matrices? Well, because there might be mixing, there might be hybridization between different states, right? So this hybridization might be physical. So if you think of silicon, for example, not only you get bonds in between atoms, that's where the electrons are localized, but you also need an sp3 kind of hybridization to capture those bonds, right? So this is from a standard textbook example. So suppressing those hybridization might not be a good idea to capture the electronic ground state of the system. On the other hand, we have learned that this U might also be understood as a simple way to reintroduce this exchange correlation discontinuity, the discontinuity of the exchange correlation function or potential into the Koopmans system. So what happens if we use this with silicon and gallium arsenide? You see that the band gap actually gets corrected, but in the wrong direction, so it gets decreased. So this is opposite to what we obtained so far with other types of material. And that's exactly due to the thing that I was mentioning, that the +U improves localization by suppressing hybridization, right? And in these materials, actually the band gap is a bonding, anti-bonding one. So it's based on hybridization. So suppressing hybridization means suppressing the band gap. And so you get in the wrong direction. And you typically also worsen other properties, structural properties like the bulk modulus or the equilibrium lattice parameter. However, if this is the problem, the fix might be quite easy. And in fact, working with the extended Hubbard model and doing the same algebra that led us to define this correction here, we came up with this extended correction that includes also inter-site interaction. So now we have both on-site interaction that tries to localize electrons on each atom and inter-site one instead that try to favor bond formations, try to favor hybridization between sites. They compete with each other, of course, so the final type of ground state or the final type of localization of electrons depends on the relative value of these two. And, but the presence of both in the same functional gives you more flexibility, so the possibility to get a more general, to describe or to capture a more general localization scheme, basically. Fortunately, these two quantities can be evaluated from the same linear response approach discussed before. This is just the off-diagonal term of that same interaction matrix, of which the U is the diagonal term. Okay, so it's nothing new, and this come out for free, basically. So how it works? Well, we tried first nickel oxide, which is a case where the standard one already works relatively well, and you get a small refinement on the equilibrium lattice parameter and bulk modulus, but the gap is of the same quality. Silicon and gallium arsenide, those are the ones that we care the most in this with this correction. And in order to capture that, you need to allow for the sp3 hybridization, as I mentioned before. So you need to allow two L channel per atom to be corrected. So far we had only one. For example, only these states to be corrected by this correction. Now we want two, and that's the extension that we made. So you get V both on-site and inter-site, basically, between S and P states. And that's the kind of results that we get. So again, this is not in perfect agreement with the experiment, but at least we correct the result in the right way. Okay, and that's true also for gallium arsenide, and you get most cases you get a significant improvement also of the equilibrium lattice parameter and bulk modulus. Yes. Yes, yeah. I don't remember if self-consistently or from one-shot calculation from the ground state. This is in this paper, this detail. I think it was self-consistent, but I'm not 100% sure. Well, this is the band structure, so you see nothing relevant really happens to the general shape that we're used to from textbooks. And the last example is how it improves the description of the localization of charge in those battery materials that I mentioned before. So you see also a significant improvement, quantitative improvement in the agreement with the experiment in the average voltage and in the way localization is captured compared to the two end members of this series, the one that with full lithium and with the one without any lithium in the composition. Same thing also for the manganese, which is actually more problematic in this sense because manganese tries to hybridize a lot more with oxygen, surrounding oxygen, than iron does. So it is more useful in this case than it was for the iron compound. Okay, so I will stop here, giving you some brief points. So the plus V is useful extension for system with significant hybridization, as I try to demonstrate. The success in correcting description of covalent semiconductors clarifies that this Hubbard-like correction can address some effects of strong correlation. So don't forget that we work with this auxiliary system of non-interacting electrons. So we deal all the time with single particle quantities. So we aim to correct the effect of strong correlation in this one particle projection on the world of this one particle physics, basically. Can be useful to capture, improve electronic localization in non-degenerate system. If you have degeneracy, degenerate ground state like iron oxide, you have to handle with care. You have to understand what you're doing. So cannot use as a black box, unfortunately, and otherwise you might end up in wrong ground states. Okay, I think this is all for this moment. Sorry for taking so long and keeping you away from the coffee break. Of course, I mean, the rest of the presentation I will do it this afternoon. It's more of a review of what we've seen and what we will see in the practical exercise this afternoon. So it's appropriate that I stop here and take any question that you have at this point. Okay. Yes.